Thanks everyone for the invitation. I wanted to be there with you, but it didn't work out, unfortunately. Maybe next time. I want to talk about how some work that we did a little bit more than a year about how one could potentially build a fault-tolerant quantum computer using cat codes as the building blocks and some outer code on top of it. So what we call concatenated cat codes. And it's a collaboration with many people. I won't read all the names, but they are here. It's a joint paper with all these people. And as a motivation, right? Like, let me just mention something that we know well, but that if one day we can build a large quantum computer, that would be interesting, because we already know today some applications that we like to run there, right? So in cryptography, we know we can run Shor algorithm and try to break RSA. And then if you do the accounting of how many qubits you need for that, you find that for 2048 bit RSA to break that, you need 6,000 qubits. Or maybe you want to do some simulation of some molecule in chemistry. And people, for example, look at this Femoco molecule, which is an interesting one. And then you get that with 200 qubits, one could do a simulation of this molecule that seems to be out of reach with our classical methods of today. And then in material science, you can try to simulate, for example, the Hubbard model that maybe can help understand high-T superconductors. And then if you want to get to some size, which is also out of reach classically, it's something like you need 100 qubits. And you can look at optimization problems, right? Like if you want to do some Grover speed up or some smaller speed up, you have many applications, scheduling, ranking, learning, and so on. And then you can start running something interesting on also like 100 qubits as well. So it's kind of, if you look at this slide, you can be optimistic about it, right? Because you don't need so many qubits to start getting some very meaningful applications of quantum computing, right? But there is a very important catch here, right? Which I put here on the bottom, which is this is assuming perfect qubits and perfect gates, right? And we don't have them. What we have in the lab is like, some error rates for each component, right? But why we think that is still, we might one day have a quantum computer, even though it's not an easy task, is because, right, in the last 30 years or so, the community developed the idea of quantum error correction and fault tolerance. So what we learn is that if you look at the error rate here in this plot, the error rate of the gates in our quantum computer, even if it, for example, take like this point here is 10 to the minus 3, so every 1,000 gates there is one which is faulty, and of course you will not be able to run this application that I mentioned before, because for these applications you have to apply billions of gates. But what is possible with error correction is to use more qubits. So instead of having one, you replace each qubit in your computation by many physical qubits. This is what we call the qubit overhead. So for example, for 10 to the minus 3, if you look the maths we have today, we need between hundreds and thousands of physical qubits to get one logical qubit, which is really good, which has like error rates, 1 in a billion, for example. And then we can run these algorithms that we know today. So this is really like a trade-off, right? So the smaller the physical error rate, the smaller the overhead that you need. There is a point when the physical error rate is so big, and that's like around 1% as far as we know, that error correction doesn't work. But then, that's the game, right, that we have to play. We have to try to decrease the physical error rate as much as we can, but we know there are limits to that, and it's unlikely that we can get to the errors required for running the applications. But then we also have to pay a price of the qubit overhead of using more large and larger codes to try to suppress error. Another question is, what is this curve, right? So this depends on the kind of error correction you're doing, right? So is there a way to get a better curve here, for example, right? So that's an important question in quantum computing. Okay, so now going back to the same slide, right? Suppose just putting that curve into numbers. Suppose we look at qubit with 0.1%, right? Which means like you can apply 1,000 gates before there is an error. So this 10 to the minus 3 error rates. which, the platform, the experiments, they are not there yet, but they are getting very close to there, right? So that's a good ballpark to have for the error rates. But now, unfortunately, it's much more challenging, right? All these examples that I mentioned before, now for factoring, we need 20 million qubits. For some simulation, at least 1 million qubits. Maybe for this like Hubble model simulations, 100,000 qubits, a little bit better. And the same for Grover. And then even Grover, you might lose the speed up, right? Because you have the overhead in time for error correction as well. So this becomes very challenging, right? And that's why, quantum computing is still something we would like to get eventually, right? But it's far in the future, right? It's not something that will happen in the near term, at least fault tolerant quantum computing. So a little bit more detail, right? So how we get this estimate, right? So let me tell you how we usually do this today, and that's using a particular way of doing quantum error correction, which is called surface code, which if it's not the best, it's close to the best way that we know how to do error correction. Once you think about this trade-off of physical error rate versus overhead required for target logical error rate. So we won't need the details, right? But just for you to remember, in case you know it, the surface code is just you want to encode 1 qubit and then encode in a lattice of d by d, where you have d square physical qubits to encode this qubit, but you also need some ancillas. Use these ancillas, right, to measure what we call some stabilizer checks. So you measure some parities, right, like the z parities whenever you have a star, and the XXX parity of the yellow stars, in a way that we can learn if there was an error in our qubit without corrupting the qubit, right? So we cannot measure the qubit directly, so we have to measure it indirectly, and we add ancillas to do that. So summing up everything, for 1 qubit, now we need 2d squared minus z physical qubits. And there is an empirical formula, this one that I wrote, which tells us how the probability of error of the logical qubit, of the encoded qubit, decreases as a function of the probability of error of the physical components, the physical, and this distance of this lattice. And it goes like this, so it's exponential the distance of the lattice, so that's nice. So it's exponential in roughly like the square root the number of qubits that we use in the code. But the prefactor, right? So the base of the exponent is roughly like 100 times this physical probability of error, and that's why we need the physical probability of error to be at least at most 1%, right? Otherwise, this doesn't decrease. But if it's less than 1%, start decreasing, and we want substantially less than 1%. Otherwise, it decreases too slowly. So then this is just a plot of this formula. If you look at, for example, this is what I mentioned, right? Probabilities of error of 0.5%, which is where we kind of are today, roughly. Then you see that to break even, right, when it gives any gain, you need like, distance 9, so you need 150 qubits. Even distance 15, you see kind of big, right? So you see probability of error of 4 times 10 to the minus 4, so there's an improvement, but not very big. Whereas if you're already like physical error rate 0.1%, it starts decreasing faster, right? And then to get to this like 10 to the minus 9 level, where the applications that we know today, we can start running them, we need what I mentioned, right? Like around like 400 physical qubits per logical qubit, which is challenging to get, right? Okay, so then this is great, right? And it's good that we have this code at least, and many people are trying just to build surface code. There is proof of principle experiments and plans on how we can scale up these experiments to try to do larger and larger surface code. That's a good game to play, right? But that's not the only one. So another idea which is worthwhile being explored is that if there is better ways of doing error correction, right? Is surface code the best thing out there, or there is more efficient ways that we can do error correction? And there is some line of work in this direction that is called like people call hardware efficient fault tolerance. And the idea here is that let's not just treat our building blocks as qubit 2-level systems and just assume there is some error rate there. Let's look more at the physics there and try to correct as much as possible on the hardware level, right? So you could also phrase this just saying, I want the best qubit possible. But as I mentioned, sometimes actually we really have to think that it's more than a qubit, right? It's a more complicated object that we can already use, right? There's extra degrees of freedom in the building blocks do some kind of encoding. So one famous example, right, is kind of hardware efficient fault tolerance is Majorana qubits that people are trying to implement in the lab. They haven't done that yet, but it's people working in the area hope that once one can implement this qubit, you'll be a kind of a topologically protected qubit. So the physical error rates there will be much smaller than what we can have today. We have to see. There is also like 0-pi qubits. It's use a superconducting qubit, but you try to also use a clever encoding that protects some kinds of error. And the one we're going to focus is like a cat qubit, which is people, of course, in quantum optics know it very well, right? So you just get a harmonic oscillator, you get like a photon, or you can get vibration, as we mentioned, like phonon, and then it's a harmonic oscillator, and you look like a coherent state there, right? So that's the classical state of light. You can also look at superposition of coherent states. Then that's like more interesting is the non-quantum states, and I will try to argue that that's actually a good way to have a qubit, because you have the whole phase space to play around, right? And then you can try to get some protection just by using just trying to encode the information redundantly in a clever way in the phase space. So the idea, as I mentioned, is that we can think hard how we can get good cat qubits to get some good protection already, and then concatenate with the surface code or with something else, but then in a way that combine the overhead hopefully is smaller than what we have today. So what is the risk, right? Whenever we start thinking about this, is that if you put excessive focus on just the building block, right, we might lose sight of the final goal, which is we want to have a logical qubit with a target error rate, which we can run some useful application that we're interested at, right? So in this paper, there's a lot of people, and in the end, it was a long paper because we tried to do this exercise, right? We really tried to think about a particular scheme that I mentioned to you, but from end to end in a sense, and really see, right, how everything comes together. And we learn it's very tricky, right? Like that it can be many dead ends, and I'll mention some of the limitations that we found as well. Right, so you shouldn't be trying to optimize T1 times or physical error rates or probability of winning a Nobel Prize because it's beautiful physics. This is great, but not necessarily the right metrics, right? So I would like to argue that it's important to have like a pragmatic approach, right? Whenever we're thinking about new architectures for quantum computers, we should be agnostic, and we have to be open to hybrid of hardware and software error correction. I think that's likely be the winning strategy, even though we might not know, right, what is the combination yet. And we should try to evaluate ideas quickly and don't get attached, right? So as I mentioned before, let's try to work backwards from some target application, right? So for example, in our study, we want to solve the Hubbard model on some 8x8 lattice. How we do that, right? Thinking about all the way from this to how we engineer the qubits. And then if you do that, hopefully we can avoid some of these pitfalls that I mentioned, right? So it might be that you have very good coherence in your physical qubits, but very bad physical gates, right? Because of crosstalk or some other issues. Or maybe, and we see this a little bit in this scheme that I mentioned, you might have bad physical gates, and then maybe you would just ignore the scheme already, right? Because there's better gates around. But actually, because there is some extra protection, you might have good logical gates, right? Or maybe you can have a logical gate set that works well, but it's not the one you need for your application, right? Or maybe everything's just too slow, and then if it's too slow, it defeats the purpose, right? The point here is to try to get speed ups. So these are some of the things that I think is helpful to have in mind when you're thinking about this problem. So what I want to do here, tell you a little bit, the last 15 minutes, is analyze this particular fault tolerance architecture, which is based on like phononics as kind of where we put the cat codes that I'll tell you what they are, and superconducting qubits because we need them to manipulate the information in this phononic modes, and using these cat codes as the building blocks. And I will tell you what we learn about it, right? And there is good news and some bad news as well. Okay, so what is this cat code, right? So they have been, in quantum optics, they go way back, like 20 years ago. More recently, but already like some time ago, they start being explored for quantum computing and for quantum error correction. And there are many variants of them. I will just mention one, the one that we use. And the one that we use is that we have two coherent states. We have coherent state alpha, and we change the phase, coherent state minus alpha. And we think about alpha like sufficiently large, not super large, but think about like alpha, like from 6 to 8, maybe 10, something like, sorry, alpha square, like 6, 8, 10, something like this. And alpha and minus alpha are not really orthogonal, but they're very close to orthogonal right in this range. So we can just say that our 0 is plus alpha and our 1 is minus alpha. As I said, not really orthogonal, but almost orthogonal. If you look at the complementary basis, plus and minus, then they're exactly orthogonal. And then you can define them plus as alpha plus minus alpha, minus as minus alpha minus minus alpha, right? So this is really like, how we really define our basis using the complementary basis. So this is just a diagram, right, in phase space, how they look like. Now, what we try to do is we have this CAT code, right? So you can think in some, cavity QED experiment is there, right? State of light, for example, as I mentioned, we look at vibrations in our case because of some recent experimental results that were interesting to us. But what usually happens is that there is noise, right? And the noise we understand well, like the main kind of noise is photon loss, right? Is excitation loss. There is some kappa 1 error rate there. Sometimes there's also dephasing. This kappa phi there. We have this master equation. But now suppose that we had a special kind of bath there. We had a bath where photons are lost in pairs. Okay, so we have like a kappa 2. And then whenever there's a photon is lost, actually 2 photons are lost, right? So this A square. And then we also put, this basically is like a 2 photon drive that we put it there. Now this is the jump, right? This A square minus alpha square is a jump term. And what you can check very easily is that this has 2 dark states, right? And dark states are exactly alpha minus alpha. Okay, so if you don't have the normal decoherence we usually have, we only have this kind of engineer bath where photons are lost in pairs and we have this 2 photon drive. Then you see that the steady state, right? This goes to some dark state steady state, which is exactly given by alpha minus alpha, our 2 code words. So our code space is stabilized by this 2 photon dissipation. And then the idea is that we can try to engineer this artificial coupling to a bath such that the oscillator only emits and absorbs excitations to and from this bath in pairs. And then we can, hope that there will be some stabilization, some protection of the quantum information here. And what we can find is that this indeed happens. So bit flips, which means here going from alpha to minus alpha, right? So they are, especially when alpha grows, they are well separated in phase space, and they become very unlikely if stabilized by strong enough engineered dissipation. Why is strong enough? Well, basically is like kappa 2 times alpha square has to be bigger than kappa 1 and kappa phi and the other decoherence processes. So we need this kappa 2 to be substantially large, but only kind of the effective kappa 2, which there is some boson enhancing, has to be bigger than kappa 1 roughly. But this is not a perfect qubit because there is indeed there is exponential suppression from going from alpha to minus alpha. So bit flip errors are exponentially suppressing the size of the cat in alpha square. But the phasing does not get fixed. So whenever you have a photon loss, there is like you can see that right a annihilation operator was applied to your states, and then you see just maps plus to minus and minus to plus. So there is a z error here. And what you can what you can find if you do the calculation is that the z errors actually increase linearly in alpha square. So there's a trade-off here. So you are gaining in bit flip, but you're losing in phase flip errors. And then you can think if it's worthwhile, and it is, because you gain here in bit flips, there's an exponential suppression, whereas in phase flip there is only a linear increase. So what are you doing? You're biasing your qubit, right? So your qubit after this, for alpha sufficiently large, your qubit has very little bit flip errors, very few X errors, have a little bit more Z, but not too many more. So then you predominantly have Z errors at this level, and you have to try to correct the Z errors by using some other codes. So that's the idea of this bias noise qubit, right? So the bit flip errors, they are much more less likely than phase flip errors. And if you do the calculation and numerically you check that, although the prefactor sometimes changes, the ratio of probability of X error to the probability of Z error becomes like exponent like this, e to the minus 2 alpha squared. Okay, so that's part of the story, and that's interesting, but that's not the whole story, right? Because think about that. Suppose you bias your qubit, and then you only have z errors, right? X errors, you can like ignore them; they are very small. And then you can think, great, because now I only have to correct z errors. Maybe even some classical codes works, right? Maybe I can use repetition code or something else. But it doesn't really work like that, right? Because whenever you have quantum gates, if you're not careful about it, your quantum gates can map z errors to x errors, right? And then after applying one gate, your error is already unbiased again, right? So now z and x errors are equally likely. So what you want is something very special, right? So you want that throughout the computation that you want to do, that all the gates you apply, they preserve the bias, right? Because you always want to make sure that we only have to correct z errors. And so that's the idea of like bias preserving gates. Some gates are clearly bias preserving, like a rotation around some like z direction, right? That's bias preserving. But for error correction and fault tolerance, the CNOT gate is an important gate. And in principle, it is bias preserving if you think about that as like a unit block, right? So you have a CNOT. These are like the Pauli Z or the Pauli X. And you can look at the propagation, right? From, this is the CNOT in the alpha minus alpha basis, right? Assuming they are orthogonal, they are pre-orthogonal. And then you can see that, what's the propagation of a Pauli error with the gate, right? How Pauli errors, you can map them through the gates. And then you see that if you have a Z in the control, it's just a Z. If you have a Z in the target, it becomes 2Z. If you have an X in the control, it becomes 2X. If you have an X in the target, it's just an X afterwards. So great, Z and X doesn't get mixed here, right? So that's very good. But that's too simplistic because physically you really need some interaction, right, to try to implement these gates. And once you really think about like the gate not as a unit block, but as coming from some interaction of some Hamiltonian and so on, there is a result that there is no way to implement a bias preserving CNOT if you only have qubits, if you only have two-level systems. So that's unfortunate, right, for trying to do these ideas of bias, in your noise model. But what Gilad and Miharimi and also some other papers on Kerr-Katz, a little bit different scheme but related, found out is that with cat codes you can have a bias preserving CNOT gates. So what you do, you just you have this two-photon dissipation that I mentioned before, right, on one of the cavities, and in the other cavity you have a two-photon dissipation, but that rotates. So if the first one, right, if the first cavity is in like alpha, then this term disappears and you just have a normal two-photon dissipation, nothing happens, right, because that's what the CNOT should do. But if the first cavity is in minus alpha, then this term disappears, and now you have a two-photon dissipation, but that rotates in time, right? The maps alpha to minus alpha and vice versa. So then you have a NOT operation. So if you can have this dissipation, you do implement a CNOT, and you can show it's bias preserving, right? Because everything is always separated in phase space, and the two-photon dissipation is always on, right? And I explained to you before that two-photon dissipation was the key to get this stabilization. So how you do that physically? You can do you can have a Josephson junction, and then you engineer this kind of nonlinear coupling, right? There's nonlinear Hamiltonian between the two cavities. I will not explain in detail. But the important take-home message here is that there is a bias preserving realization of the CNOT gates. So then what this offers also proposes to say, okay, let's then create a logical qubit in two steps, right? So let's correct X errors first using the CAT code, using the two-photon dissipation, some kind of autonomous error correction, right? Because there is engineered BF, so we just suppress the error. And now we have to correct Z errors. Let's correct just the Z errors using a classical code. And what's the simplest classical code? Is just a repetition code, right? So it's Z errors, so we have to use the plus minus basis. We just repeat it many times, n times. So our logical qubit is, we have this plus cat state, right? Alpha plus minus alpha. And we repeat it n times, for example, 3 times in the simplest case. And for the plus logical state, we have like alpha minus alpha, and repeat it n times as well. And how we do the error correction here now, I will just measure the parity of neighbors, right? So we measure x1, x2 here on the first and the second, and x2, x3 on the second and the third. We see if there is any, if it's ideal code word, we always get +1 eigenvalue. If it's -1, we have an error, we correct. So this kind of repetition cat codes, right? that's kind of a circle that you use to measure it with CNOTs and measurements. And this is a plot that we did, right? Where we do here, we have the logical error rate of our logical qubits. We vary kappa 1 over kappa 2, right? So kappa 1, if you remember, that's kind of the decoherence you have there is photon loss. You want to fight that. Kappa 2 is this engineered dissipation that we do. And then, you find something like this, right? We found you can get, for example, 10 to -7 or so error rates, right? Depending, with some distance like 9, if the kappa 1 over kappa 2 is sufficiently small, right? And then there's some threshold around, like the ratio has to be at least like 1,000 or so for this to work well. I'll put this more into context very soon. But now let me just tell you what is the physical model that we use here, when we did our analysis. So how we do the cats, right? That's the first question. And in our analysis, we chose to do the cats. We could choose to do the cats using some electromagnetic cavity, and the analysis will be somehow similar. But we chose to use this phononic bandgap resonators. So they have been, developing in Armin Savav Naemi lab and also in Oscar Painter lab. And they work with us right in this project. So we're getting knowledge from them about them. And they're still early on. They're less developed than ENM cavities. But there's some nice things about them if you think about scalability. They're very small. They're like nanoscale size. Usually they have little crosstalk because of that. And for example, in Oscar Painter's lab, they measure in silicon, if you create this, right? So they quantum information, just some vibration of this one-dimensional cavity. They measure they are microwave, so that's important because you want to couple them to superconducting qubits. But they have very long coherence time, up to 1 second, which is huge if you think about the microwave regime, right? There is a catch here, is that once you couple them to the qubits, to the superconducting qubits, then that's way lower today. But then at least as like a limit, the potential we can go there one day. It's like a very promising. My time will be up, so I have to run here a little bit.
So how Fernando, we then? You have like 3 minutes.
Yes, thank you. Yes, I'll try to finish in 3 minutes. So I will go a little bit fast in this slide. So just to give you the flavor, how we want to manipulate these cats, right? So if I go back here, this is like this is a harmonic oscillator, right? So there is no way to manipulate this to create a cat here. So we need a non-linear, right, element to manipulate this cat, for example, to do the 2-photon dissipation, right? So what we do, we engineer Hamiltonian between, A is the annihilation operator of the phononics, right? And B is the creation operator, B dagger of some what we call dump modes. And then we do some kind of nonlinear optics between them, right, by using a nonlinear element, which is a just for junction. So that was done recently by Lescan in Lecter's group in Paris with ENM cavity, electromagnetic cavity. This is what we call asymmetric threaded squids, this gadget here. And then we just take this design from them, but then we look at the numbers with the phononics and so on, and we try to analyze what we get. And a nice thing from the experiment, they did see this kind of exponential suppression of X error rates in this ACS up to some point. Then there was a saturation, but the saturation is also understood, right? So they started with lifetimes of a few microseconds and went up to the way of X lifetime of 1 millisecond. So that's when you increase the photon number. So that's an interesting experiment. I will have to not explain to you that. Let me get to some conclusions. We put everything together, but a lot of our work that I didn't explain actually was how we do error correction in this sense, right? So in error correction, we have to think about like the gates that we use for error correction, but also how we do the logical gates. Usually we need what we call magic state distillation to get a universal gate set, and we really try to tailor everything to this case of bias noise, right? And that's where most of the novelty of our work was. I'll have to gloss over it. But then what we did is also the estimate cost, right? So we look at, what is the cost of all the components that we have. In our case, the most important number, the components that we counted was the number of ATSs, because these ATSs is where we send a control line there, right? So these phononic cavities, they are there, but they are passive. For example, we use alpha square equals 8. We use kappa 1 over kappa 2 of like 10 to the -5, which is very small. I'll comment on that. but why we chose that? Because that gives a probability of a CNOT gate of roughly 4 times 10 to the minus 3, right? So that's close to this surface code comparison we had before. And then we found some under these numbers, and I have to discuss these numbers, but let me just tell you the results. If you assume these numbers, and if you look, for example, for this Hubbard model application that we want to run, we found that the number of ATS required, which is like our counterpart to Qubit, is like 34,000. Okay, so that's still a lot, right? But that's like an order of magnitude better than the estimates from before. So we found that there is some potential substantial gain in going to this. We don't usually use repetition code because they're not enough. We have to correct some X errors, but we use what we call a thin surface code. So the surface code, asymmetric surface code. There is a catch, and the catch is that this scheme really, will work well only when kappa 1 over kappa 2 is very small, like 10 to the minus 5. And definitely, and that's why we want to look at phononics. If we can get to this like 1 second or even like milliseconds lifetime for the phononics, we can get to this level. But we're not there today, and it might take a while to get there, right? So this is challenging. So what we found is that there is promise for substantial overhead savings here, but at the same time, to get good gates using cat codes, to get good CNOT gates, for example, you require a high level or either very small photon loss there or some very strong engineered dissipation there. And today is not possible to get there, but maybe one day it will be. So that's like the good and the bad of the scheme. So the conclusion, I told you a little bit about a scheme that we analyze that we think, we thought, but we still think, although there's some trade-offs, it's promising for reducing overheads, but there's these challenges. What are the challenges? Is that right now this bias preserving CNOT gates that we use is very slow, and then this means that we need very small kappa 1 over kappa 2 to be effective. That's a challenge. So it'll be good to look at alternatives for this. There is a potential multiplexing that I didn't mention, but we use some multiplexing to put many phononic cavities, at least like 2 per ATS, right, to save in the number of qubits that we need. That was one of the reasons we wanted to look at these phononic cavities. But we found that there is like a lot of crosstalk effects, and we have to be very careful about it. So that in the end, the gain is also limited, although there is some gain. And there are our building block, right, which is this very high-lived phononic cavities. So they have great lifetimes by themselves, which is promising, but we have to couple them to a transmon, right? So we have to couple vibration to electromagnetism. How we do that? We need a piezoelectric coupling there, a piezoelectric film. And once we do that, this is a problem for our friends in the lab. It's still very, it becomes much more lossy. So they still have to figure out ways to get this very long coherence time for the phononic cavities coupled to a ATS by piezoelectric coupling. So there is a lot of work to be had, but we still think that might be a promising candidate, and we are excited about looking at these possible variants and seeing how we can improve things there. So let me stop here. Thank you very much for your attention.
Thank you. Thank you. We have a question. Please wait for the mic.
Hello, Fernando. Thank you very much for your talk. Quick question. You said that this bias preserving is not possible with qubits, right?
Yes.
So first, in one sentence, why is it so? And second, if I have ancilla with change dimension, is there any, say, estimate of error with respect to dimension?
Yeah, good question. Good question. So, I mean, with qubits, it's something like they use some kind of like a little bit of Lie algebra that you'd say. Okay, so I don't have a one sentence answer, but basically there's not enough space, like in the just a 2-level system. You kind of have to move around in some other dimension, right? So to always preserve the information. So I don't really have a good answer to that now. But the second question, there is a very good answer. Indeed, you can do approximate bias preserving in any finite dimension, and I don't know what is the ultimate scaling, but I know that the level of bias, the approximation of the bias is like exponential the number of dimensions that you use. So So cat codes are convenient and are nice, but indeed you can just have a lot of levels, and you can have maybe a transmode using many levels, and then maybe you can also get something interesting. Although, like on practical level, I don't know any scheme where you can actually do that. People are looking at Fluxonion, trying to do approximate bias preserving gates there, and maybe there'll be some good results, but I don't know yet.
Other question, please.
Yeah, so hi Fernando, it's Rafał Dymkowicz-Dobrzański. So
Hi, Rafa.
thanks for a great talk. So I have a question, because you focused on this ratio kappa 1 to kappa 2, and you said as if it was the only condition, but if we go with alpha too large, I guess something will go wrong. So can you comment on how do we choose alpha optimally, and why can't we choose larger ones?
Yeah, great question. So because I told you that there is like a threshold for the value of kappa 2 that we need, right? So we need kappa 2 bigger than the kappa 1. There is this ratio, of course, right? But actually it's there is also alpha squared that gets in the picture. So this is the dominant one that's like for the CNOT gate, and indeed the kind of the fidelity of the CNOT gate is independent of alpha squared. But there's other moments in the computation, for example, when you have kind of idling errors where the rate of loss increases linearly with alpha square, right? Although kappa 2 is still there, so that's fine. Along the actually scheme, sorry, I take it back. So in this scheme, Rafa, ideally, actually, if you could go to large and larger alpha square, you would gain. But what happens is that you cannot go, right? So if you go to very large alpha square, then you start exciting some levels that you don't want to excite, right? In your ACS, for example, right? So you need a lot of power that you cannot have in the experiment. So actually in this scheme, alpha square is try to go to as high as you can, but we know that in practice you won't be able to go there, right? And that's why we choose alpha square, like 8 in this analysis, because there was this Lescano experiment, for example, they went there and they didn't find anything problematic. So so it's really like what's the highest alpha square that you can go before you start breaking down, for example, this interaction that we have, right, using the Josephson junction, right? At some point it will not work anymore, right? Or you excite some levels that you don't want to. So that's the limitation of alpha square here.
Great, thank you. Other question? Peter, you have a question this time?
Yes, I do. Yes, thank you. Thank you. It was a very nice talk. I want to follow up on Rafal's question about alpha, because I know from the quantum optics situation, where people make these Schrödinger kittens, they are essentially using an approximation. So while it looks a lot like alpha plus minus alpha, it's actually like they snip away a photon. And so it looks a lot like it if you plot the Wigner function, but it is actually different. Do you know, or have you an expectation of how precise you need to be able to make the cat states?
Well, I mean, I don't think it has to be very precise, because that's what you care about is your information being delocalized in phase space sufficiently, right? That you have this X protection, like, right? That's the alpha and minus alpha, they are two L's which are very far away, right, in phase space, right? So if you have any perturbation around this one and around this one, as long as they don't get close together, you still think that the information will be preserved there, right? At least the bit flip, which is what you care about. So that's why, right, you kind of have this robustness there, right? Because you can have a photon loss effect, right? That you can have a dephasing that would kind of change your cat, but the information will still be preserved, right? Because they are far away in phase space. So I would expect this robustness, and this is what they see in the experiment, indeed, right? So they run this experiment, right? And of course there was all kinds of imperfections there, but they saw this like more than 200-fold improvement, right? In X kind of T1 lifetime, right? So it actually worked well there. What are the limits, right? And can we really push this even more? I don't know, right? And then indeed one has to be careful about the final level of details.
Thank you.
Okay, great. I think there are no more questions, and in any case, the time is over. Thank you. Let's thank Fernando again.
Thank you. Thanks, everyone.